Okay, so you guys have fun with the Ian last Thursday, having a class with him. So while you guys have a fun time with Ian, I went to Boulder, Colorado. So this is Boulder, Colorado. So I had a couple of meetings with my colleague in the National Center for Atmospheric Research, which is located right here under the mountain. In case you're forgetting season, it's a season of the winter is coming, so you can see the trace of snow, and then Rocky Mountain National Park is the behind of this local mountain here. So Saturday, one of my colleague and friend at Stony Brook University, he has his own plane, and then he's doing some research with this plane, kind of air sampling, things like that. So he brought his plane to Boulder, and then he offered me a scenic ride with this plane. So that's his plane. And then this is a sampling device. And then we hit the runway in Saturday morning, beautiful Saturday morning. And then plane got crashed on the runway. So fortunately, I survived. Really? And then John is fine. John is right here. And then the reason I show you this photo is that, I got lucky. Maybe you guys got lucky. If something happened that you guys 4 weeks of the hard work kind of gone. If I died or something, so this was your lucky day, all right? So feel lucky, all right? So we talked about it's late October, so winter is coming. So we are right here, and then we will just take a look at the news coverage that happened yesterday in Harbin, China. So let's take a look at this news coverage before we start our class. What's going on? Okay. Yeah, this is not good. Let's try again. We may need to watch the commercial again, but whatever. So this is the, before we actually watching this video clip, so this is kind of big kind of London type smog event out there. And then if you read this news article, what it is saying is that, let's see where it is. So it's talking about PM 2.5. It's obviously particle pollution. And then there's a coal burning heating system. That sounds familiar. It's about the London type smog again. And then they are burning crop. So burning again. And then there's a lack of wind. So that's high pressure system. So it's combination of emission and then meteorology too, right? So let's watch this coverage.
The two face masks. It's quite simple because it's basically just like this term, magic tape here. Mm-hmm. And China's smog.
So my idea is to always obviously already taken.
Imported from the US, it's designed to filter out harmful particles and gases for long-term health benefits. You can't go back in time, right? If you go back in 10 years, okay, we're in lab. The damage is done. Yeah, it's already done. The difference between a blue sky day here in Beijing and a polluted one can be dramatic. Right now, it's rated as very unhealthy by the US Embassy monitoring site. But in Harbin in northeast China, the pollution is off the charts. Dense, acrid smog brought this northern city of 10 million to a standstill. Schools are shut, dozens of flights cancelled, highways closed. Visibility down to almost zero. Pollution 40 times the WHO recommended standard. The local government blamed it on Harbin's coal-powered central heating, turned on over the weekend. But critics say China's pollution is a terrifying side effect of the country's decades-long obsession with growth. Wary of social unrest, Communist Party officials have announced new stringent measures. They want to meet their own acceptable standards by 2020, WHO standards by 2050. You have to breathe in through your nose and... That's good news for Lao's growing business. He's struggling to keep up with demand, catering to all kinds of tastes, selling a product for the new reality of China. Do you think people are getting used to wearing something like this? I think it's okay. It's a reality that could last for decades. David Mackenzie, CNN Beijing.
Well, already business is out there, but it's hard time to keep up the demand. So you can just, you have a good idea, just go for the business. So that's what's going on in the world out there. And then this is what's going on, what will be going on next week. But at the same time, today, there will be a midterm, so October 29th during the class, right? And then a summary note will be uploaded by tonight. So I already finished to finalize the midterm questions. And then there will be no multiple choice questions. And then I will go over this summary note this Thursday, all right? And then there will be 10 points of the extra credit questions. And then because I will be out of country between basically this Saturday to next Wednesday, so I will extend my office hour this Friday, 9 a.m. to 5 p.m. So if you have any question, feel free to visit my office this Friday, all right? Any other questions about midterm? Ready? Not even prepared? Anything? You have plenty of time.
Yeah.
No question? Okay. So we have talked about chemical reactions of gases and particles. That's about the air pollutants, right? And then from today's lecture and the next one, we will discuss about how those air pollutants are moving around in the atmosphere. So this is kind of an iconic photo about studying chemical reactions that is happening in the atmosphere in the context of air pollution. So as a chemist, I call myself as a chemist, and then what we are interested in is that what's going on in the atmosphere in terms of reaction. So we assume that atmosphere is a sort of chemical reactor, and then we are studying chemical reaction in gas phase and particle phase happening in the atmosphere. Basically, we can make the small glass bulb like this, and then we can make the chemical reactions, just like what's happening in the atmosphere. But if you think about the Earth, anybody knows about the radius of the Earth? 6,400 kilometers. So a diameter is 12,000 kilometers. So this is not good at all. Let me use mine. So diameter of Earth is 12,000 kilometers. So let's assume this is Earth. This is center. So this is 6,400 kilometers. Anybody knows that height of the atmosphere or troposphere? Anybody? Any guess? 10 miles? 10 miles is a good number, 10 kilometers, let's say. So 6,400 to 10 kilometers, what's the fraction of this thing? Probably something like this, right? So atmosphere is like this big, surrounding the Earth, right? And what's the size of the car with respect of this thing in terms of pollutant emitter? Kind of a tiny bit of the point. Probably this point is probably over-exaggeration if you think about the scale, right? So all those pollution is happening very, very tiny scale. And then atmosphere is kind of big chunk of air surrounding the Earth, although it is very, very thin layer compared with the Earth's radius, right? So basically, what I want to say is that very different from, where is it? From this glass bulb. Basically, in glass bulb, if something is happening, it's going to be mixed up pretty quickly. But in this kind of big picture of what's going on in the real atmosphere, then air pollutants actually kind of transport is very important because our pollution emission happens really, really tiny scale, and then our atmosphere is quite big dimension of the in terms of space, right? So emission and then reaction in the atmosphere is one thing, and then how those air pollutants are transported in the atmosphere is another thing, right? So we will discuss about how air is moving around in the atmosphere. Basically, that dictates how air pollutants are transported from one place to the other place, okay? So we'll talk about high pressure, low pressure system today, and then today mostly we will talk about horizontal airflow in the atmosphere. So to understand air movement in the horizontal scale, we need to understand about 4 different forces, but most important forces is the pressure gradient force, Coriolis force, and then friction. So let's discuss about that pressure gradient first. So whenever we watch the weather forecast on TV news, the weather person usually talk about how high pressure system is coming, low pressure system is coming, things like that. So that's basically same term that we were using when we discussed about ideal gas law. So high pressure is basically that ideal gas law is PV equals nRT. And then let's arrange this equation with respect to pressure. So high pressure, low pressure is all relativeness, right? Higher pressure or lower pressure, right? So basically, if we assume temperature is same, volume is same, then what dictates the higher pressure and lower pressure? Which is, so this is constant, right? So it will be dictated by N, which is number of molecules in the atmosphere. So high pressure system and low pressure system, if you assume just like that, and then there will be more number of air molecule in higher pressure system region than the low pressure region, right? So what's going to happen? Air molecule is going to be moving from high pressure system to low pressure system, right? It's pretty straightforward, right? So that's basically pressure gradient. So basically air is going to be moving from high pressure region to the low pressure region. So that's pretty straightforward. But so the story is not that simple because air, the toward Earth is rotating. So we need to factor in this Earth's motion into the air motion too. So because it is a little difficult to imagine kind of an Earth scale rotation just with a whiteboard. So let's watch this video, which is pretty good on to explain how Earth's rotation is affecting air motion.
In this view of Earth from space, it is clear that the Earth is rotating. However, as an observer on the surface of the Earth, the only indication our planet is rotating is in the observation of the sun during the day and the stars during the night. Every day, the sun rises in the east and sets in the west, but we are completely unaware that we are traveling to the east at hundreds of miles per hour. So just how fast are we moving? Well, at the equator, the rotational velocity of the Earth is an incredibly fast 1,018 miles an hour. If you were to travel from the equator to about 30 degrees north latitude, the rotational velocity would have slowed considerably to about 882 miles an hour. Well, why? Well, as you walk north or south from the equator, you're actually getting closer and closer to the Earth's axis of rotation. Because the surface of the Earth is solid, the rotational velocity will decrease as you walk north or south from the equator, because you're actually getting closer and closer to the Earth's axis of rotation. To understand this better, let's imagine that we take the Earth, a sphere, and flatten it out into a rotating disk, like a merry-go-round. If you were to stand on the edge of the merry-go-round, the rotational velocity would be large, and you would feel like you're going to fly off. However, if you stand in the middle, the rotational velocity would be much less,
and you would feel like you're barely spinning at all. Now, what if we were to have two people sit on opposite sides of the merry-go-round and try to throw a ball to one another? You can see that as the ball leaves the hands of the person throwing it, it becomes independent of the rotation of the merry-go-round, and therefore follows a straight path. But because the person trying to catch the ball is still rotating with the merry-go-round, they are quickly moved out of the ball's intended path. Because the merry-go-round is spinning counterclockwise, this deflection is to the right. If it were spinning clockwise, the deflection would be to the left. Now, to an observer above the merry-go-round, the path of the ball appears straight. However, to people on the merry-go-round, the path of the ball curves to the right of the intended motion. This experiment demonstrates how the rotation of the merry-go-round appears to cause a deflection in the path of the ball. This also demonstrates how air movement on the Earth's surface can be deflected by the Earth's rotation, a phenomenon called the Coriolis effect. How do we relate the effects of the Coriolis force to air motion in our atmosphere? To answer this question, let's first investigate what would happen to a parcel of air that was initially at rest with respect to the Earth. At 30 degrees north latitude, the parcel is traveling to the east with the Earth. But if we were to shove this parcel at 10 miles an hour to the north, what would happen to its motion? We have already seen from the merry-go-round experiment that the ball would be deflected to the right. But why? The answer lies in understanding something called the conservation of angular momentum. Angular momentum is the product of the mass times the velocity times the radius of a rotating object. The conservation of angular momentum tells us that for a rotating object, the product of its mass, velocity, and radius is constant for that system. Well, what does this mean? Think of a ball swinging around on a string. If you shorten the length of the string, the rotating ball spins faster. Angular momentum, however, is conserved because as you decrease the radius or the length of the string, the velocity or the rotational speed of the ball is increased so that the product of the velocity times the radius times the mass stay the same. As an example, let's consider a ball that weighs 1 kilogram on a string that is 1.5 meters long, spinning at 5 meters per second. When we calculate the angular momentum, we find its value is 7.5. If we shorten the string, we know that the ball will spin faster. So if the radius of rotation is reduced to 1/2 meter, the rotational velocity must increase to 15 meters per second so that the product of the mass times the velocity and radius remains at 7.5. Now, how does all this apply to this parcel that we shoved north? Well, as we moved it to the north, the rotational speed of the Earth will decrease. However, because the parcel of air is actually moving closer and closer to the axis of rotation, its rotational velocity must increase by the conservation of angular momentum. If you were standing at 30 degrees north and watching the parcel as it moved, it would appear to be deflected to the right. This apparent deflection is the direct result of the Coriolis force. What is really interesting is that if the parcel continues to be deflected, it would trace out a path along the Earth's surface that kept its original speed of 10 miles an hour constant with respect to the rotation of the Earth. Therefore, the path of the parcel would eventually trace out a circle, much like the path of this baseball on the merry-go-round. Watch as Amanda pushes the ball out to the center, and it makes a complete circle back to her other side. Some important facts about Coriolis force. First, the Coriolis force causes objects to deflect to the right of their intended path in the northern hemisphere, and to the left in the southern hemisphere. This is why low-pressure systems like hurricanes and extratropical cyclones circulate counterclockwise in the northern hemisphere. Second, the Coriolis force affects the direction of an object, not its speed. Third, the strength of the deflection is proportionate to the speed. For example, the faster an airplane flies, the more the pilot must adjust the flight track to account for the Coriolis force. And finally, the Coriolis force is 0 at the equator and maximum at the poles. To leave you with an interesting fact, the effects of the rotation of the Earth are negligible at very small scales. For example, if a pitcher were to throw a pitch at Wrigley Field to home plate at 100 miles an hour, the deflection of the path of the ball is very small, only about 900 microns, which is about 0.9 millimeters, or about the thickness of your fingernail. However, for an intercontinental ballistic missile, if shot a few thousand miles at 1,000 miles per hour, the deflection is hundreds of miles.
So that's basic summary of the Coriolis force. So how many of you actually heard about Coriolis force before? Maybe about 1/3. So this is not really a familiar concept. So basically the bottom line is that the air motion is triggered by this pressure gradient from high pressure to low pressure system. But once it starts to move, then because Earth is rotating, it is affected by the Earth's rotation. And then we call that force as Coriolis force. So basically, as the person on that video explained, the Coriolis force is always exerted to the right-hand side in northern hemisphere, and then left-hand side in southern hemisphere, right? That's all you need to remember. And then, so this is kind of a summary again. So from northern hemisphere, if a pressure gradient is line is dictated air motion from this point A to point B here, because of the Earth's rotation, it will be diverted a little bit towards the right-hand side again. And then the same thing from here to here, it is also diverted to the right-hand side due to Earth's rotation, okay? So among of you that already heard about Coriolis force, and then have you guys heard about this rotation of the drain? The water is circulating here. It's governed by the Coriolis force. How many of you actually heard that theory? Most of you? That's wrong. That's bogus theory. And then as the video explained, that Coriolis force only affected on large scale phenomenon, not this kind of a small scale phenomenon, okay? So that's the only thing only a force that affects on the large scale phenomenon like high pressure system or low pressure system, which at least a couple of 100 kilometer motion of the air or whatever, but not this kind of a small scale problem. So if you want to know further about this, then you can just read this website. This is a kind of website written by a meteorology professor at Penn State University, and then he attacked a couple of the misconception of the scientific kind of misconception among the public out there. It's kind of surprising, actually. I even in South Korea, I even thought that this is affected by the Coriolis force, but that's not right. That's simply wrong, so wrong about it. So that's one thing you need to remember. And then the other thing is that Coriolis force is only start to affect on the motion once motion gets started. So if some object is standing still, there's no Coriolis force is affected on there. So we need some mechanism actually initiate air motion. In this case, pressure gradient. Initiate the air motion. Then once it is air motion initiated, and then it is kind of a large scale, then it is affected by the Coriolis force. So that's the thing you need to remember for the Coriolis force. So let's go ahead. Again, summary. So because of the rotation, the northern hemisphere going right, and then left and left. Okay? So let's put together this pressure gradient and then Coriolis force all together, right? So basically, let's assume this is high pressure system, and then as you can see, the pressure gets lower, this line. So this is the same pressure. This is the line indicate the same pressure. So pressure out here is a high pressure towards the low pressure, right? So because of this pressure gradient force, the air motion is initiated right here. And then once it starts, then Coriolis force will be affected, right? Then air will be moved to your right-hand side, if we assume this is northern hemisphere. Then finally, it just balances between the pressure gradient and Coriolis force, and then it will just follow this pressure gradient line, right? So we call this air motion as geostrophic wind, set like right here. But as you saw that video clip, So Earth is rotating and then Earth is round. So once usually this pressure gradient line is the round shape. So another another two forces we need to consider. Once it is making the rotation motion like this, centripetal force and centrifugal force, but those two forces also balance each other. So it just makes this circular motion. So this kind of wind, geostrophic wind, is going to be happening if Earth is flat, but Earth is round. Now the high pressure and low pressure system are making this circular motion. So if we assume this is the center of the low pressure system, then obviously the high pressure is going to be outside of this pressure system. So the pressure gradient initiate air motion towards from high pressure to low pressure side. And then if it is northern hemisphere, what's going to happen is that it's going to be turning right like this, and then making this geostrophic wind, which is following pressure gradient line like this. If you are math geek, you can solve this equation to actually visualize this thing. But probably not many of you guys are math geeks, so ignore this equation, all right? So this is a low pressure system case, and then a high pressure system case, that air is going to be moving from high pressure to the low pressure. And then when air motion gets initiated, and then air motion is going to be affected by Coriolis force, and then it will turn right, and then making this circular motion, right? So this is geostrophic wind, okay? So again, this is summary. It's turning clockwise. Is that clockwise? Yes, clockwise in high pressure system, and then counterclockwise in low pressure system in the northern hemisphere. It's going to be exact opposite in southern hemisphere, right? And then this is air motion that we assume that there's no friction. So air motion that is happening in the high altitude, like 5 kilometers above the surface or 10 kilometers above the surface, there will be no friction between the air masses and then air masses. But if you assume the air motion in the surface, then there's significant friction between air and then land surface. So basically, friction is that force. If you want to move this block to this side, and then friction is going to affect it to the exact opposite direction of the actual object is moving, right? So that's basically the reason we can walk on the surface. We use the friction actually, then we can walk on the surface, right? And then if there's no surface, and then we cannot walk, so even the polar bear is going to be just sliding away here and there if there's no friction. So friction is kind of important thing so to maintain our life. And then if we use the friction to stop the car, right? So brake system is pretty much the thing that we use the friction, and then it just stop the wheel motion of the car, right? So friction is important thing. We often forget about the friction, but friction is happening all the time. Even we just walk around the campus or anywhere, right? So so depends on the surface. There's a high coefficient of friction. That means that so if you just exert the same amount of the force to the object, if your surface has higher efficient of the friction, then actually you ended up moving shorter distance, then the surface has lower coefficient of friction. So that's kind of a way to quantify that friction. But what only you need to remember from this class is that there's always friction between air and then surface. And then that's going to be affecting air motion of the surface, all right? So this is the summary of the friction force that affects on the air motion above the ground. So geostrophic wind is right here. So geostrophic wind is the wind that is happening up in the air, maybe 1 kilometer above the surface, 2 kilometers above the surface. But on the very surface, due to this friction force, it is not really parallel to this pressure gradient line. Rather, it is moving a little bit towards the low pressure side. So air motion is going to be moving towards the low pressure side. If you consider balance between a pressure gradient force and then Coriolis force and then friction right here. So this is another summary that on the surface it's going to be moving towards to the low pressure side. And then if you take a look at the high pressure and low pressure system, then this is actually blocking this figure. Then due to friction on the surface, air is moving towards the low pressure side. So if we have a low pressure system right here, air is going to be on the surface. Air is going to be moving towards the low pressure center, right? And then what's going to be happening is that if air, this is all about the air molecule, it's moving towards the specific point like that, then there's going to be more air is accumulating on the surface. Then air is going to be moving up from the surface so that more air can be rolling into the low pressure center, right? So in the low pressure, there will be upwelling air motion. It's going to be happening. And then what's going to be happening in the upwelling of the atmosphere is that up there, temperature is lower, right? Then condensation is happening. Then you can expect cloud formation. And then usually it's associated with the rain, things like that. So that's why whenever the low pressure system is rolling in to the, even in the Southern California, there's a cloudy day, and then rain is associated with it because of this upwelling motion. And then in high pressure system, air is going to be moving out from the high pressure system, from the surface, right? Then some air should be fill this void because air is moving out from this high pressure center. So what's going to be happening is that air is coming from the top, upper atmosphere, and then subsidence is happening. So that's why we usually observe the clear day in the high pressure system, right? So this is high pressure system on the surface and then low pressure system on the surface. And then so difference between geostrophic wind and then surface wind is that due to friction, air is moving into the low pressure system, then moving out from the high pressure system. Okay? This is not working. Yeah. Here we go. So again, this is summary that little bit towards the low pressure side, and then this is a little bit towards the low pressure side. So air is going to be coming into the low pressure side center, and then air is moving out from the high pressure center. But if you take a look at the direction of the arrow, again, just as same that high pressure system, air is rotating clockwise, and then low pressure system, air is rotating counterclockwise. Okay? So this is a real world example that usually there's multiple high pressure and low pressure system. Usually the low pressure system over the ocean associated with the rain because of the it contains a lot of humidity in there, and the low pressure system is associated with the upwelling motion of the air. So maybe twice a year we have a rain in Southern California. Most of the cases, this low pressure system over the Alaska, especially during the winter time, rolling into the Southern California, that actually caused some rain event in Southern California. And then this low pressure system is expanding usually towards the in the Pacific Northwest region, like Seattle and Oregon, place like that. So that's why they have rain all the time from October to the April because of this low pressure system out here in Alaska, right? So if you understand at least how surface low pressure and then high pressure system working, then you can understand pretty much what's going on in terms of grand schematic things in the weather system over the United States. So again, this is another kind of photo show that how air is moving in the high pressure system and the low pressure system over the surface. So air is going to be moving out from the high pressure system and then going into the low pressure system. So what I want to expect you guys is that if you just see this photo by itself, then you can just throw some arrow of the air motion that air is going to be coming out from the high pressure system. And then you should know that direction of the air motion that caused by the Coriolis force. All right? So that's it. And then, so let's take a look at now a little bit of a three-dimensional motion of the air. We talked about the horizontal air motions. Now let's discuss about some vertical air motion. So let's assume Earth is just like this, and then sun is right there, and then it is just heating up in the middle. Then equator region is going to be hotter than the polar region, right? Then what's going to be happening is that there's a convection going on because this is hotter, air is lighter, and then it's going to be going up. And then some other air in the polar region, because it's cold, will be filling in this space that because air is moved from the surface to the above. And then that causes this circular motion, right? So basically, this is the initial thought about the air motion, and then we call it Hadley cell. So the scientist name called Hadley first developed this concept. So this is going to be the air motion. So this is the that Hadley cell model. So in the equator, air is moving up. And then this in the upper atmosphere, then air is moving towards the polar region like that. But due to Coriolis force, right, this air motion from this equator to the polar region is going to be to your right-hand side. That's why this air motion is the backside of the arrowhead, right? So arrow, right? So if you assume arrow just like that, so that's basically arrow is kind of from here to the screen, right? So that's why we just rotate this thing like this. And then if air motion is coming from this screen to your side, then it just looks like this, right? So due to Coriolis force, the air motion from equator to the polar region is going to be moving towards your right-hand side. So this is what actually so the origin of the jet stream. In the upper troposphere, very fast air is moving from, let's see, this is the, where is the east and west? So this is the west to east motion, right? And then on the surface, because of this sinking air in the polar region, moving towards the polar, to the equator, and then air is also affected by the Coriolis force, then it's going to be moving out from the screen, right? Right? So on the surface, there's an easterly wind there, and then on the top of the atmosphere, there will be a westerly wind that is going through the screen, right? At least in the northern hemisphere. The southern hemisphere is everything is opposite. Okay? So this is basically a Hadley model of the air motion of the Earth, right? Confusing? Too easy? You guys looking very bored, get bored by that. Maybe you guys already heard about this thing, or don't care about this thing or something. But let's make it a little bit complicated because you guys look very bored by this simple model. But Earth is big, right? So Earth is so big, so this Hadley cell that initiated in the equator cannot actually move all the way out to the polar region, right? It is just making one cell in the 1/3 of the Earth's surface in the northern hemisphere. So basically, this is Hadley cell right here. That is, if it is small enough, Earth is small enough, then there will be one cell, which is Hadley cell, can happen. But Earth is so big, so one cell is happening here, then the other cell is sitting in the mid-latitude region, and then there's another cell is going on in the polar region. There's 3 cells in each hemisphere. So overall, there's 6 cells over the Earth. So we call it Hadley cell, which is near to the equator. So this cell actually makes this jet stream, which is air is moving from to this side, right? So from west to the east, and that's the in the upper troposphere, upper air, and then what this cell makes the surface wind is that because air is moving from higher latitude region to the lower latitude region, like this, and then due to Coriolis force, air is going to be moving to your right-hand side, like this. Now we call this wind as trade winds, right? And we call this the ferro cell, which is because air is sinking right here, and then air is going up in this latitude region. So, and then in this cell, surface air is going to be moving from south to the north, and then due to Coriolis force, it will be veering to your right-hand side. And then again, here, there's another jet stream is coming in the about 60 degree north and 60 degrees south, okay? And then finally, there's a polar cell right here, and then make another easterly winds. So this is overall wind distribution over the Earth that is mainly caused by sun is locating in the equator region. So obviously, this is very conceptual model. And then let's go to the real world example. So this is January pressure distribution. Let's go back this thing again. So I didn't explain the low pressure and high pressure distribution here. So because air is moving upward, so this is by definition low pressure region, right? In the equator region. That's why over the equator there's rain all the time, because this permanent low pressure system sits in the equator region, okay? And then about 30 degrees north, what we call high pressure, permanent high pressure region. And then because there's a sinking motion of the air exists right there, so there's a permanent high pressure system usually located about 30 degrees north or 30 degrees south, either way. And then in the 60 degree, again, there's upward motion of the air cause low pressure system in the about 60 degree north or 60 degrees south region, okay? But the real world picture is kind of mimicking this conceptual model, but it is a little different. So let's take a look at why it is a little different, right? So this is surface pressure distribution over about 40 years. So from 1959 to 1997 in January, and this is in July, right? So this red line right here is basically low pressure system, and then basically this line right here, right? So why this is fluctuating like this at first? Let's discuss about it first. Anybody can guess why that is kind of going north and south? Like, it's not really straight line like this to make our life complicated. Maybe that's it, but anybody? Season? Yeah, actually, seasonal change is that this one and this one is seasonal differences. This is January and this is July. So this is basically our winter time distribution. So first of all, this is a little bit south than the geographical equator, right? This line right here is a little bit south, because in January, sun is where? A little bit towards the southern south of the equator, right? So sun is going to be sitting right here. So this line, center line, moves toward the south side, right? That's pretty clear. And this kind of fluctuation is happening due to distribution of land masses. So over the ocean, so water, you need more energy to heat it up, right? But the land, you need less energy to heat it up. So that actually makes some differences in terms of the air motion too, because air motion is pretty much dictated by pressure system. And then if you think of this ideal gas law, different pressure will gives you different pressure, different temperature. Sorry about that. Different temperature will gives you different pressure. So this land mass and then ocean distribution make your, at least not your life, our life, make very complicated as a scientist studying Earth. So and then if you take a look at the high pressure system distribution and the low pressure system distribution, at least in the southern hemisphere, it's very consistent with this conceptual model, right? You have high pressure system about 30 degrees south, and then low pressure system, consistent low pressure system in the 60 degrees south, right? But in the northern hemisphere, it's a little more complicated. We have a high pressure system right here and then low pressure system right here. It's especially in the winter time, it looks like I agree with this conceptual model. But in the summertime, which is in July, we cannot really see this low pressure systems right here. And then if you take a look at this big chunk of massive land, the high pressure system usually observed during the January, and then low pressure system is observed during the July in the summertime. So this high pressure system and then a low pressure system over the land is pretty much caused by land gets hotter during the summertime. That causes the low pressure system. So if you imagine that there's land mass and then sun is right there, then land, as I said, there's less energy to heat it up. So land is going to be heated up during the summertime in July. Then what kind of air motion is going to be happening? Upward air motion. And then that's by definition low pressure system. So this low pressure system over the land is during the summertime, and the high pressure system during the winter time is caused by kind of this land, the temperature kind of differences between the summer and winter over the land. And then that makes this pressure system real complicated. And then this low pressure system is same thing too. So in the low pressure system during the winter, summertime, because this land over the Northern American gets hotter, so this high pressure system get expanded. So this low pressure system that caused by this general circulation model is moved toward the northern side. And in the winter time, this low pressure system gets expanded to a little bit towards south. Again, this low pressure system in the North Pacific actually cause a lot of rain in the Pacific Northwest, like state of Washington and Oregon. And sometimes this expanded to the Southern California that makes a rain in the Southern California too. So the bottom line here is that there's a permanent high pressure and low pressure system out there. And then due to the land mass heating and cooling, there's a kind of temporary high pressure and low pressure system is evolved, depends on the season. Okay, there's a permanent low pressure, high pressure system, and then temporary seasonal high pressure, low pressure system is happening in average. And then those kind of high pressure, low pressure system affecting our weather, also air pollutant transport phenomena. So we will discuss about it later towards the lecture or course. So this is summary. So this is semi-permanent pressure system that is caused by this general circulation. So in 45 to 65, there's always low pressure system, and then 25 to 45 north, there's high pressure system, and then there's thermal high pressure, low pressure system that I explained. As I explained, usually during the over the land. During the summertime, there's low pressure system because of this convection of the air, because land gets hotter, the air is moving from the surface to the atmosphere that cause the low pressure system. So that's what we call thermal high pressure and low pressure system. And then implication towards the air pollution is that usually low pressure system reduces the air pollution, and then high pressure system enhances air pollution. Okay, if you remember that London 1952, the London big smog episode, it mentioned about high pressure system is sitting over the London, then there's a very calm and clear day caused the accumulation of the air pollutants over the surface, right? And then we watched the video clips a couple of 2 weeks ago, the Beijing early this year. That was very calm day and clear day, and then caused that accumulation of air pollutants over the surface. Again, the video clip that we watched this class, also the high pressure system was sitting over the city, and then air pollutants accumulated over the city's surface, right? So this is the example. And then usually low pressure system associated with the rain and then high winds, so air pollutants can spread out. And then high pressure system right here is kind of a push to the downward to the air. So kind of the depth of the air motion is shrinked in the high pressure system compared with the low pressure system, and the high pressure system usually associated with calm day, so air pollutants can be accumulated over the surface. So that's kind of how the weather system and then air pollution is tied into one thing, right? So this is bottom line. Again, summary slides about the air motion. Maybe this is not the last slide. So basically this equator right here basically blocks the air mixing between northern hemisphere to southern hemisphere. So if you go back to this plot again, so sun is right here, and then because of this kind of a motion of the upward motion of the air near the equator, basically this blocks the air, the pollutants mixing from northern hemisphere and then southern hemisphere. So it takes a really long time for air pollutants or other atmospheric constituents to mix from northern hemisphere to the southern hemisphere. So it takes about a year to mix the air between northern hemisphere and then southern hemisphere. So let's assume that air pollutants, that lifetime is far less than 1 year, and then that's only emitted from the northern hemisphere. Then, according to this time scale, then that specific air pollutants cannot be observed in the southern hemisphere, because this air circulation model dictates that it takes about a year to actually completely mix in the northern hemispheric air and then southern hemispheric air. And then if your air pollutants lifetime, chemical lifetime, is far much shorter than 1 year, then that specific air pollutants cannot be transported from northern hemisphere to the southern hemisphere, right? So that's how you can relate with the lifetime of the air pollutants and then this time scale of the air motion from one specific region to the other specific region, right? And then in terms of interhemispheric motion, so it usually takes a few months in this north to south motion. But this westerly motion, so from North America to Europe, Asia to the US, it is much, much more efficient. It takes about 2 weeks from air masses transport from the west to east side, right? So this is because of the older air motion, if affected by the Coriolis force, also the jet stream. So that's why that people in the west coast of the United States complain about the air pollution from China or Korea or Japan, mostly China because China is the big country. And then also, although we are not really listening that much from these complaints, but all those Europeans complain about that air pollutants transport from the east part of the US because it is much more efficient transport of the air pollutants from the west to the east side. Okay, so even in the Far East Asia, actually I kind of involved with the research about kind of international air pollutant transport. If you think about this China, Korea, and Japan out here, it is just size of about half of the U.S. If you take a look at the border between the big cities. So I think west part of the China is mostly mountain, and then most of the Chinese population located in the east part of their country. And then if you take a look at this part of the world, it's quite a small land masses, and then the time scale that air pollutant transport from one country to the other country, for example, from China to Korea, because air motion is always from, in a grand schematic, from west to the east. So actually the air pollutant transport from China to Korea, and then Korea to Japan, and then China to Japan, it usually takes like few hours to few days. So they kind of always fight each other that our air pollution gets worse because of your country, things like that. So those kind of a thing is happening because air motion is always from west to the east side. Okay? So this is what the air motion, how air motion dictates air pollutant transport. Okay? Clear? So this is another example of the why meteorology and then this time scale is important to understand air pollutant distribution over the Earth. So this is CO2. We already took a look at this plot, at least this one right here. So basically from 1960, so this is Mauna Loa, Hawaii, which is northern hemisphere, right? It has been increased past about 50 years, right? And then it has been increased due to increased fossil fuel use by people. And then we can see this kind of a annual cycle right here. So if you average over, we see the highest CO2 concentration about April, at least in the northern hemisphere. And then October is the lowest point of CO2 in the northern hemisphere. And then there's an annual cycle right here. It's caused by the vegetation activity, or the photosynthesis, usually active during the summertime. So CO2 is absorbed by the vegetation and then released by the vegetation during the winter time and the summertime, right? We discussed about this thing. And then this is one point observation in the northern hemisphere. And then after Dr. Killing started this experiment, this network of CO2 observation has been expanded to everywhere over the Earth. So now we compile the data of the CO2 concentration distribution all over the Earth. So basically this color coding is concentration of CO2, right? So this dark color right here is low CO2 concentration, about 350 to 390 ppm. And then wake up. Now time to wake up. I told you that I already finished to compiling the midterm, right? So you gotta wake up now, because this is a very important thing you need to remember to prepare your midterm exam. So this is a CO2 concentration. And then this is equator right here. So this is equator right here, right? And then this is northern hemisphere from 0 to 90. And then 0 to 90 south. So this is southern hemisphere. So this is from 96 to, let's take a look, how many years? 2005. So what is the most striking thing you can see out here? Can I? Yep, go for it.
The equator is getting more and more carbon dioxide.
Equator is getting more and more. So if you follow this line right here,
Yeah.
so basically the increasing trend of CO2
Yeah.
It's everywhere, right?
Yeah.
So,
It's,
mhm.
it's really going up in the north more than the south.
Yeah. So, northern hemisphere is higher than southern hemisphere in terms of CO2 concentration. So why is that? Let's go back. Here. So why northern hemisphere CO2 concentration is higher than southern hemisphere?
There's more land, more people, and more activity.
Yep. Do you agree?
Oh, yeah, and because it takes a year to come.
Yep. So CO2 emission, where is it coming from? People, right? So where's more people living? From over the land, right? We cannot live over the surface of the ocean, right? So there's more people, obviously, in the northern hemisphere. So more CO2 emission is happening in northern hemisphere, and then it takes about a year to move the CO2 into southern hemisphere. So you can actually really observe that time scale of the air mixing from this plot, right? So any other thing you can observe here? Any other? No. So this fluctuation between winter to summer in the northern hemisphere and southern hemisphere, where is the fluctuation in the which one is bigger in northern hemisphere or southern hemisphere? So northern hemisphere is bigger, right? Why is that? So if you think that, so basically this is, let's say this is December, this is January, and then northern hemisphere is just like that, and then southern hemisphere is gonna be exactly opposite because it is kind of a different season, northern hemisphere and southern hemisphere, right? And then if you take a look at this amplitude of the fluctuation, so if you take a look at this, you can get the information, best information out of it. The amplitude in the southern hemisphere, it's southern hemisphere and northern hemisphere. It's much less in southern hemisphere. Why is that? Small vegetation over the land, right? So from the one plot, you can get a lot of information out from the one plot, and then you can tie, this is chemical observation, but still you can tie into this one chemical observation with totally different kind of thing, which is air mixing time scale, right? So this is kind of beauty of science, that you can connect from one thing, seemingly totally different from the other fact, but this, you need two facts at the same time to understand one simple observation. This is not simple, one observation, okay? So specific heat. So this is fancy word, but if you take a look at what that word's meaning, then that's not really big deal. You can easily answer what that is. So what you gotta do is take a look at this unit, right? Joule is unit of energy, and then kilogram is unit of mass, and then Kelvin is unit of temperature. So basically what this means is that specific heat means is that amount of energy for given mass to take increase the temperature of the 1 Kelvin, right? So for example, water, it takes a lot of energy to increase 1 Kelvin of temperature, okay? If you take a look at the number. But for example, dry sand or clay, which is basically land, it takes less energy to increase 1 Kelvin of temperature compared with water, right? So that's what you can learn from these numbers. Yep?
If it takes less energy, does that mean it has a smaller specific heat or a greater specific heat?
Smaller number means that takes less energy because,
So it has
yeah.
smaller specific.
Yeah, so basically this is right here. So this is energy, which is joule per kilogram mass, which is kilogram in here. then temperature Kelvin. So if you want to increase one Kelvin of temperature, whether you need higher energy or less energy, kind of thing, right? So basically, land needs less energy for temperature increase. If you think the other way around, then if there's the same energy is given to land and water, then land is going to be heated up much faster than water, right? So from this number, let's take a look at how this thing will affect on the air motion. So you have land here, temperature 2, water here, then water has higher specific heat, right, than the land. So during the daytime, sun is up, then which temperature is going to be higher? Over the land, temperature 2, over the ocean, temperature 1.
Stop. Turn it off. Oh, there it is. No, it's
Who doesn't have the eye clicker today? Everybody has eye clicker? 1, 2, 3, 3.
compare which one.
Would you?
Which one is hotter?
Hey Ian, would you do some? How many students are? Would you count how many students are here?
Yeah.
Just try to compare the number that I got and then how many eye clicker responses that we actually have today. Confusing? I thought it's pretty straightforward. So A is temperature over the ocean is higher than land. B is same. And then C is temperature over the land is higher than temperature over the ocean. And the specific heat of the land is much less than over the water, right? You don't need to even think about that specific heat. What you do when it gets hot over the beach, you jump into the water, right? Why you are doing that? I got all the answer. 68. So how many students doesn't have the eye clicker? 3. I think we missed 3 people here, so we need to figure it out who those 3s are. So let's take a look at the answer. Oh, so there's B. Same. And then mostly C. Okay. So yeah, I gave you the answer, right? So why you jump into the water? Because land is hotter than the water, right? Then let's take a look at. Let's discuss about a little fancy way, right? So specific heat over the land is less than the water, right? Which means that it takes less energy to increase temperature over the land than the water. And then in theory, that over the surface of the land, over the surface of the water, takes the same energy, right? And then if you take a look at the temperature increase, then over the land, temperature increase should be higher, right? That's why over the land, temperature is higher than the over the oceans, right? So this will cause the circulation of the air, which basically that empty space. So during the temperature 2, temperature 1, this is higher. So air out here is lighter, then it's going to be moving up, right? Sea air breeze, sea land breeze is happening during the daytime. It's no, it's not really high pressure. Yeah, you can understand that way, but it is kind of a little bit kind of a local scale phenomenon. That's why you usually gets the wind, even in the sunny day, high pressure day, that usually wind from the sea is blowing into the land during the daytime. Okay? This is kind of a small scale circulation near the beach. All right? Let's do it again just for fun. What's going to be happening during the night? So cooling is same thing, right? So cooling of the land is going to be much faster than the water, okay? That's one thing you need to remember. So temperature of the water and then temperature of the land. Which one is higher? We have 62. One more. It was 62 just before. We tried to mess up with me. All right, 61. I will stop this. Still 10 people doesn't get it. Okay, let's try again. So sun goes away, right? Then these two are cooling down, right? Water and land. And then you got to think about this thing the other way around, right? It's going to dissipate energy. So basically, water can contain more energy than the land, okay? So basically, water can keep more energy. So the cooling down over the water is much slower than over the land, okay? So usually nighttime temperature is the other way around. Then what's going to be happening? The other direction of the circulation during the night, okay? So this is why, in general, you can join, during the night that the wind direction of the beach is from the land to the ocean, and then during the time from the ocean to the land. So we will discuss about implication about land-ocean circulation after the exam, and then Thursday we will discuss about we'll discuss about the summary slide that I will upload tonight, and then there will be exam next Tuesday.